Picture the inside of a star. Right now, somewhere out there in the Milky Way, a sun is burning at over 15 million degrees Celsius at its core. Nuclear bombs are going off every single second, fusing hydrogen atoms into helium with a force that makes every weapon humanity has ever built look like a party cracker. You'd reckon that's about as violent as the universe gets, wouldn't you? Turns out you'd be dead wrong. Because right here, right now, in the empty space between your hands as you hold whatever device you're watching this on, something is happening that makes the inside of a star look like a calm Tuesday afternoon. And the man who proved it won a Nobel Prize. This is the physics of quantum vacuum energy, and it is, without question, one of the most mind-bending things Richard Feynman ever touched. So who was Feynman? If you know the name, you probably know the personality first. The bongo drums, the safe cracking at Los Alamos, the legendary Caltech lectures. But behind the larrikin charm was arguably the sharpest theoretical mind of the 20th century. In 1965, Feynman shared the Nobel Prize in Physics, awarded specifically for his fundamental work in quantum electrodynamics, or QED, with deep ploughing consequences for the physics of elementary particles. That phrase, deep ploughing, is the Nobel Committee's way of saying this theory went all the way to the bedrock of reality. QED is the theory that explains how light and matter interact at the most fundamental level. It describes every push, every pull, every flicker of electromagnetic force you have ever experienced in your entire life. And hidden inside this Nobel Prize-winning framework is a discovery about empty space that Feynman himself found deeply troubling. Because quantum electrodynamics for beginners sounds complicated, but the core idea is actually this. The universe has fields everywhere, and those fields cannot sit still. Let's build this up properly. In classical physics, the physics of Newton, the physics of your high school textbook, a vacuum is nothing. Remove all the matter, cool everything down to absolute zero, and you get genuine emptiness. Silence, stillness, zero energy. But in the 20th century, quantum mechanics rewrote the rules, and one of those rules is the Heisenberg uncertainty principle. You cannot simultaneously know the exact energy and the exact timing of anything at the quantum scale. This isn't a limitation of your measuring instruments, it's a fundamental feature of reality. And this one principle has a wild consequence. Even empty space cannot have exactly zero energy. If it did, you'd be measuring both the exact energy, zero, and the exact time, right now, which the universe simply will not allow. So the vacuum, what we call physics of empty space, must always have some residual energy jittering through it. This is what physicists call zero-point energy physics, and it is very real. Now here's where Feynman's Nobel Prize theory does something extraordinary. Quantum field theory, explained in its simplest form, goes like this. Every type of particle in the universe, electrons, photons, quarks, corresponds to a quantum field that stretches across all of space. When you see an electron, you're seeing an excitation of the electron field, like a wave on the ocean. But here's the thing. Just like the ocean never stops moving entirely, those quantum fields never go to zero either. They fluctuate constantly. And those fluctuations, according to QED, produce what are called virtual particles. What is vacuum energy? It is precisely the energy of these virtual particle fluctuations, popping in and out of existence everywhere in the universe all the time, including in every cubic centimetre of space you've ever been in. This is not speculation. This is backed by some of the most precisely confirmed predictions in all of science. Here's the proof, and it's elegant. In 1948, the same year Feynman was revolutionising QED, A Dutch physicist named Hendrik Casimir made a very strange prediction. He said, "Take two uncharged metal plates and place them extremely close together in a vacuum. Classical physics says nothing should happen. There's no charge, no field, no force. But virtual particles, explained through quantum vacuum energy physics, tell a different story. The plates restrict which virtual photons can fit between them, lowering the energy density between the plates compared to the outside. The imbalance pushes the plates together with a measurable force. And in 1997, this was confirmed experimentally with extraordinary precision. The Casimir effect is a measurable, reproducible, real-world demonstration that empty space is seething with energy. Feynman diagrams explain simply. Those iconic squiggly line drawings you've probably seen were actually the mathematical language Feynman developed to calculate exactly these kinds of virtual particle interactions. Every Feynman diagram, every squiggle, represents a different way that virtual particles contribute to the energy of the vacuum. So back to our opening question. Why is the quantum vacuum more violent than any star? Let's put the numbers on the table. The surface of our sun burns at around 5,500 degrees Celsius. Its core hits 15 million. The most energetic processes we can observe in the universe, gamma ray bursts, neutron star collisions, release energy densities in the range of 10 to the power of 20 joules per cubic metre for fractions of a second. Now consider the quantum vacuum. When physicists calculate the theoretical energy density of the quantum vacuum using quantum electrodynamics, using Feynman's Nobel Prize framework, they get a number. And that number, depending on the energy scale you calculate to, ranges from around 10 to the power of 9 joules per cubic metre using conservative electromagnetic estimates, all the way up to a staggering 10 to the power of 113 joules per cubic metre when you push the calculation to the Planck scale. The vacuum of empty space, on paper, contains more concentrated energy than any star that has ever burned or ever will burn. Every single point in empty space is, theoretically, a site of incomprehensible energetic activity. Virtual particles explained through this lens are not gentle little quantum ghosts. They are the residue of an energy density that dwarfs anything in the visible universe. Now, you might be thinking, if empty space is that violent, why don't we feel it? Why isn't the universe tearing itself apart? And here is where we arrive at what is genuinely called the worst prediction in the history of physics. When cosmologists measure the actual energy density of the vacuum, using observations of the universe's expansion linked to what Einstein called the cosmological constant problem, they get a value roughly 120 orders of magnitude smaller than the theoretical QED calculation. That is not a rounding error. That is the single biggest discrepancy between theory and observation in all of science. Something is cancelling out almost all of that vacuum energy, and we have absolutely no idea what. It's like calculating that a bomb should level a city, setting it off, and watching it blow out a single birthday candle. Feynman himself, in his Nobel lecture and in his later writings, was profoundly uncomfortable with the infinities that kept appearing in these calculations. He called the renormalization techniques used to tame them, his own techniques, the ones that won him the prize, a dippy process, a trick. He knew something deeper was going on. This is the razor's edge where modern physics sits. Quantum field theory, explained at its deepest level, tells us the vacuum is saturated with energy. The cosmological constant problem tells us we can only observe a tiny fraction of it. Quantum vacuum energy is real. The Casimir effect proves it. Zero-point energy physics is real. Experiment confirms it. But the gap between what we calculate and what we observe points to something profound that we haven't discovered yet. Some physicists think the answer lies in string theory. Others look to loop quantum gravity, Some think the universe is self-tuning in ways we can't yet describe. What Feynman's Nobel work ultimately gave us wasn't just a set of calculations. It was a window into a layer of reality that operates below everything we can see. A quantum vacuum, where the fabric of space itself is never, ever still. So next time you walk through a room and see empty air, remember, you are moving through a field that by some theoretical measures contains more energy per cubic centimetre than the core of any star. It's just that the universe, for reasons we don't yet understand, keeps almost all of that energy hidden from us. Almost. Because the Casimir effect is real. Virtual particles are real. Feynman was right. And that makes the silence of empty space the loudest thing in the universe. If this blew your mind, smash the like button, subscribe, and hit the bell, because we go this deep every single video. Drop your questions in the comments below. I read every single one. What do you reckon is hiding in the vacuum? Let's talk about it.